Hello, good morning all. Today we are going to start with the topic of linear transformations. But before we start with the linear transformations, let us begin with a few questions, a few topics that we were doing yesterday itself. Okay, yesterday I was teaching you something regarding bases, dimensions, and all those kind of thing. Today also I'm going to start with that only, and then as I go ahead, we'll see. Okay, we'll see what is linear transformation, and please understand linear transformation holds a great importance in physics also. Okay, the question says, let us start with the question. It says that let W be a subspace of M2R, that is a set of matrices of order 2 with real entries, such that the entries of the first column add up to 0. We want to find the basis of W. We want to find the basis of W. So see, as you know, that yesterday also I told you what is basis. Basis is that set. So what is a basis? Basis is that set which is one, which is a linearly, in which the elements are linearly independent, and secondly the span of V. Let's say if I'm saying that B is a subset of V, and we want to say that B forms the basis for V. B forms the basis for V. So what are the conditions? The first condition is that the elements of B should be linearly independent, and also the linear span of B must actually it actually generate V, should actually generate V. So for example, I told you, let us say 0 comma 1 and 1 comma 0, or 1 comma 0 and 0 comma 1 are the basis for R square. In fact, they are the standard basis of R square. Okay, one of the example. Okay, similarly we also saw that 1 comma minus 1 and minus 1 comma 1 are also the basis of R square. Okay, let us start how to do this particular question. Okay, so we have seen that W is a subspace, and we want to see that if the entries of the first column are 0. So for example, I'll take a what is kind of pen is this? Okay, so I'll take this. So let us say that this is my matrix A, and this matrix is, let's say, A, B, and let us say C and D. If the column sum, the first column sum is 0, then it implies that C should be equals to minus of A. It implies that A should be of this type: A, minus A, B, and D. And clearly it belongs to set of matrices with real entries, 2 cross 2 set of 2 cross 2 matrices with real entries. Okay, now how to generate this? How can I generate this? How can I generate this? So for example, if I have to generate A minus A, so I can write this way. Okay, if I want to generate this B, then I will have to write this 0, 0, 1, and 0. And if I want to put, if I have to bring in picture this D, then I have to write this. Otherwise, I will not be able to generate this kind of matrix. So in order to generate this kind of matrix, I have to write this. Okay, is that clear? Is that clear? Okay, and also if you compare it with 0, 0, 0, 0, you will clearly see that if their linear combination is equal to 0 only if A is equal to 0, B is equal to 0, and D equal to 0. What does it imply? It implies this matrix, and this matrix form linearly independent set of vectors. They form a set of linearly independent vectors. So I can say that for this A, the basis would be what? The basis would be this 1, minus 1, 0, 0, comma 0, 1, 0, 0, comma 0, 0, 0, and 1. I hope it is clear. Okay, now let us move to further question. Okay, next question. Okay, so next question says what? The question says that uh, let W be a subset of M2R such that A is equal to A transpose, and trace of A is equals to 0. We want to write the basis for A. We want to write the basis for W. We want to write the basis set for W. Okay. Now just think about it. And I'll take your time, a little bit of time, and then I'll start with this question. I'm giving you a minute, precisely a minute. Try to do this and try to think about it. I'll do it for you. Don't worry. Okay, are you getting my point? So this is what this is clearly the. I'll write it here so that it will be good for you. Clearly see that this A transpose equal to A means what? We are talking about the subspace of symmetric matrix. We are talking about subspace of symmetric matrix with trace 0. With trace 0. This is one thing that you should remember. Okay. Now you see, if I'm saying that, okay, sorry, it is M3. Okay, it is M3. Sorry. Okay, this is M3. My mistake. Okay, so if it belongs to a subspace of symmetric matrix such that trace of A is equal to 0. Okay, then how to write the basis? Let us do it. Let us do it here. So what does it say? Let's say I'm writing my matrix A as A, B, C, D, E, F, G, and A. Okay, and this is A, B, C, D, E, F, G, H. Okay, I should have not taken I. Chalo, koi na. Okay, and since we know that A is equal to A transpose, so things will become easy for us. So let us take the matrix in a very simple form. Let us say it is um, A, I'll write it here now, BC. Here I'll write ABC. Okay, that would be easy. And then let's say I'm writing D here and E here. So if I'm writing D here, D would come here. If I'm writing E here, E would come here. If I'm writing F here, F would come here. Okay, so this will become your case since A is equal to A transpose. So this will be a better thing to look at. So this is the matrix that we are looking at right now. Okay, it is a symmetric matrix clearly. It is a symmetric matrix. Okay. Okay. Now, further, we also want to know that the trace of A should be equal to 0. So, trace of A 0 means A plus B plus C should be equal to what? 0. Or simply, I can write B is equal to minus of B plus C, right? A is equal to minus of B plus C. So, if I want to write this way, so the matrix A would consist of minus of B plus C, and then you have this D, and then you have this E, and then you can write D here, and you can write B here, you can write F here, E here, F here, and C here. So where B, D, E, F, and C, all of them belongs to real numbers. Okay. Now we want to write the basis for the same. We want to write the basis for the same. So first get rid of this nonsense, this thing. So what I'll do, I'll write minus 1, 0, 0, 0, 0, 0, 0, 0, 0, and then I will write C here and minus 1, 0, 0, 0, 0, 0, 0, 0, 0, and then I will write plus D so that I can get settled with this. So this would be 0, 1, 1, 0, 0, 0, 0, 0, 0. Okay. Then I will get rid of this E. E would be equals to what? E would be equals to this 0, 0, 1, 0, 0, 0, 1 0 0, and then I will write f. F would be f times I think 0 0 0 0 0 1 0 1 0. So in totality, the basis of v would be 1 2 3 4 5. So basically the dimension of this particular subspace would be 5. The dimension of this particular subspace would be 5, and the basis set would consist of all these kind of matrices: minus 1 comma 0 comma 0 0 0 0 0 0, and then you have this. Okay, not 5 even. They're going to be 1, I guess. Okay, I made a mistake here. Okay, so this b remains here. So for this is this you have to do, because see, b comes here also, no? B comes here also. So therefore 5 is the right answer. I'll write this here: minus 1 comma 0 comma 0 0 0 0 0 0 0. This is, and then you have this 0 comma 1 0 1 0 0 0 0 0, and then you have this matrix 0 0 1 0 0 0, and then you have 1 0 0, and then f times what? This matrix. This would be 0 0 0 0 0 1 and 0 1 and 0. Okay, so this will form your basis set. This forms your basis set. Is that clear to you? I hope it is clear. Okay, now let us take a few easier questions. Okay, like I feel that okay, instead of doing three-dimensional case, let us do two-dimensional cases. So we have discussed the space of subspace of symmetric matrix. Now let us discuss the case of. I'll have to take new sheet, I guess. Okay. Okay, so let me take. Okay, so let me wait for a minute, otherwise it will get crashed. Okay, so I hope everything is visible to you. Okay, so okay, so let us discuss. We have already discussed this thing. We've already discussed. We've already discussed subspace of symmetric matrix. Now let us discuss subspace of skew symmetric matrix. Okay, subspace of skew symmetric matrix. Okay, and let us take an easier case. Let us take an easier case. Let us take 2 cross 2 matrices. Okay, let us take 2 cross 2 matrices, and I hope everybody knows skew symmetric matrices are ones where A transpose is equal to minus of A. And let us say that A is a subset of, let us say A is a subset of M2R. Okay, so A be the subset of M2R, and we know that with regards to skew symmetric matrix, always there would be this kind of thing, or this would always be there. 0 0 0 0, this particular matrix 2 cross 2 will always be there in A also. Okay, it would belong to A, because you know that O transpose, if I want to take, it is equal to minus of O. So clearly this is contained in A. Also, that if you want to take some two element, I'm just showing you those people who have missed the classes of subspaces. So let me just show you that if I take A belongs to this skew symmetric space, then it will be A transpose would be equal to minus A, and B transpose will also equals to minus of B. So if I add A if I take A plus B, whether it belongs to, okay, let me take some other one. Let us say W, and let us say B. Let us take two of the matrices W and B, and let us see that whether their linear combination also belongs to their linear combination also belongs to A or not. Okay, this is how we see. See, whenever you have to prove a subspace, you just take W1 belongs to a subspace, W2 belongs to subspace, and see whether W1 plus W2 also belongs to subspace, and the scalar multiple of W should also belong to W. If this is the case, then we say that our W, that is capital W, is a subspace. Okay, so what I'll do, I'll see that whether W plus B also belongs to A. So what I have to do, I have to take a transpose. So W plus V transpose is simply equals to W transpose plus V transpose. And I know that W transpose is minus W and it is equals to minus V. So clearly I can say that W plus V belongs to A. Also you can see that if alpha is like if alpha I have to multiply it with some matrix uh, let us say W, what should I say? Okay, so let us say take some matrix, let us say B, and if I multiply it, and I know that if I multiply it with B, and if I take a transpose, what I'll get? I'll simply get alpha into B transpose. I know minus of B. What does it imply? It implies alpha B transpose is equal to minus of alpha B. It implies if alpha belongs to field F or real number in this particular case we are talking. So we know that alpha times B, if it belongs to subspace A, that is a subspace of skew symmetric matrix. If B belongs to a subspace of skew symmetric matrix, then alpha B also belongs to the subspace of also belongs to the uh, set of skew symmetric matrices. So therefore, both of them validate. So therefore, I can say that clearly the set of skew symmetric matrices form for a what I can do for a subspace. I hope it is clear. Please let me know in the comment section if there is an issue till now. I thought just to make you revise all those things. That is why I did it. What do you think the dimension would be? What do you think the dimension would be? What do you think the dimension would be? I hope everybody is listening to this lecture. Please let me know if there is a doubt. Actually, I went quite. So, what do you think the dimension for the subspace of skew symmetric matrices would be? Oh, just let me know. Okay, good. So, okay, so that is good. Now, if I want to see the subspace of skew symmetric matrix, and if I want to assess the dimension, what am I supposed to do? I am supposed to first write the basis set. What would be the basis for this? What would be the basis for this? So, as you know that if I want to write this A B C D here, and I know that the matrix is such that uh, if I take a transpose, it becomes minus of, let's say this is A, and according to the skew symmetric matrix, I know that A transpose must be equal to what? Minus of A, right? So my A transpose should be equal to minus of A. It implies A, B here comes and C, D comes here, okay? It should be equal to what? It should be equal to minus A, minus C, sorry, and then minus B and minus of D, right? This is how it should be. So what does it imply? It implies that my A should be equals to minus A, which implies what? Which implies A should be equal to 0. And also that oh, this is not the case. A, B, C and D, right? A was this. A is simply A, B, C, D, right? So A would be equals to minus of A, B would be equals to what? Minus of C, or you can say that C should be equal to minus of A, whichever way suits you, and also that D should be equal to 0. Okay, so what are we talking about? We are talking about these matrices. So what are these matrices? The matrices are of the type 0, 0, B and minus B. What do you think the basis would be? So clearly this entire space, this entire subspace subspace of, you can say, skew symmetric matrices with real entries, okay, with the real entries, skew symmetric matrices would be spanned by, would be would be spanned by what? Can be spanned by simply this. Sorry, 0, 1, -1, and 0. So what would basis be? Basis would only contain this single matrix. And what do you think I should write dimension? So my dimension of such a space would be equal to simply 1. Is that clear? Okay. And now again, let us revisit for your sake. Let us compare and revisit. Let's say because I did for 3 cross 3, let us do it for 2 cross 2 and understand for all those people who have not attended the lecture for subspaces. Let me just do it for you so that you'll be able to understand what I am up to. Okay. So please remember that the dimension for the subspace of a skew symmetric matrix would be simply will all that particular dimension would be 1, and the basis will only contain one one element. Okay. Okay, good. So, and we just did a little bit about that the dimension for the skew symmetric matrices was 3. Just sorry, the dimension for the subspace of, if you remember, the dimension for the subspace of skew symmetric matrix was 3, right? So let us confirm it all over again. All those who have joined, please mark a presence on the comment section so that I may be knowing whosoever has joined. Okay. Okay. So again, let me uh, tell you what is a subspace. So for subspace, what you need to do, let us say you have a 0. So for example, I'm saying that W forms a subspace of V. W forms a subspace of V. Then the 0 vector in W, or you can say the additive identity in additive identity in V. Sorry, additive identity in V uh, must be in W. Secondly, if I take elements from W, let's say W1 plus W2, then it should belong to W. Okay, that is a closure must hold with regards to vector addition, and with regards to scalar product also, it should be there. Okay, so if these three properties are satisfied, or even if this is dropped and if this is satisfied, at times I use this when I have to negate anything. Let's say I'll negate a few more things. But in next example I'll show you that this is also an important thing. Let's keep this also in mind. And also, if you don't want to get into all these things, just prove that, let's say W1 is an element of W, W2 is also an element of W, then alpha W1 plus beta W2 should belong to W. If you're able to prove this also, then also you can say that W is a subspace. I hope I have made myself clear with regards to subspace for all those people who have joined today. Okay. Okay. Now see, if I want to create, if I want to say that my this matrix A, which is which is a subset of uh, 2 cross 2 matrices with real entries, and let's say these are symmetric, that implies A transpose is equal to A. We want to find the dimension, although I have proven it earlier for 3 cross 3. Just want to remind you so that I'm doing it for 2 cross 2 also. Okay, please do remember that for skew symmetric matrix, the entire space would be spanned, like the subspace of 2 cross 2 matrix can be spanned using one single basis vector. Do understand? So dimension for the subspace of the skew symmetric matrix is simply 1. What do you think the dimension for the skew symmetric dimension for the sorry, not skew, okay, subspace of, okay, symmetric matrices would be 3. So dimension for the subspace of symmetric matrix would be 3. Okay, for skew symmetric matrix the dimension is 1. Okay, so let us start. So I know that 0 matrix, clearly you take 0 transpose, you will get always 0. So clearly 0 matrix is contained, and do understand that this 0 matrix is also an identity. It is an identity which belongs to M2R. Okay, so this additive identity, that is the 0 matrix, is also contained in the set of the symmetric matrices. This is first condition, that is clear. Now you see, if you take one matrix which is A, whose transpose is equal to A, you take another matrix which is B, whose transpose is equal to B, then clearly A plus B transpose will also be equal to A plus B. This is clear. And secondly, you can say that if alpha, if I multiply with A and I take a transpose of it, it will be alpha times transpose, and I know alpha A. So it implies alpha A transpose is equal to alpha. So both of these conditions are verified. The scalar multiplication is verified, and also that the vector addition is verified. So I can say that the set of symmetric matrices, that is A belongs to M2R, such that A transpose is equal to A. This set forms a subspace. This matrix set forms a subspace. Now let us try to find the what you can say the what should I say? Let us try to find that whether they form. What is the dimension for them? What is the dimension for them? So let us take a matrix A, B, C, D. It implies what? A transpose should be A equal to A. It implies A, B, C, D must be equal to A, B, C, and D. If I am not wrong, okay. What does it imply? It implies A should be equal to A. That is fine. Let us take A equal to 1 for simplicity. It implies that B should be equal to C, and it implies D should be equal to D. So let us take D is equal to 1. So, okay, let us take D is equal to 1. So life would be simple for you. So in order to generate this, what I would do, I will take the help of A. This is this matrix. Then I will take the help of this matrix, which is simply if I write B or C, one and the same thing, 0, 1, 1 and 0. Okay. And the another matrix would be D, which is 0, 0, 0 and 1. Okay. Via this, I can always so this forms your basis. This is your linear span. Okay, this is your linear span. So your basis set would be what? Basis set would be comprising 1, 0, 0, 0. Basis set would be comprising 0, 1, 1, 0, and basis set would be comprising 0, 0, 0, 1. So what is the dimension? So dimension for the subspace of the symmetric matrix would be 3. I hope it is clear. Okay. Okay, now a simple question, a very simple question I'm going to ask, and then we'll move on to some different other concepts so that it does not get very boring. Otherwise, what if we take D to be 0? Okay, so Bharat says that what if we take D to be equal to 0? Okay, so let's say if I take D equal to 0, right? This is what you're asking, right? So if I take D is equal to 0, then I'll get A, 0, 0. Okay, so let us first write the matrix A, B, C, and 0, right? Uh, okay, and if this is the case, okay, एक मिनट ऐसा करते हैं, ठीक है? And if I want to take so the student is asking whether if I take D equal to 0, then what? Okay, so if I take D equal to 0, and if I want to make the matrix, then uh, it's like a generalized case. No, just let me help myself. एक minute though. A transpose would be equal to what? It would be A, B, and C and 0. Okay, then what I can say? Okay, then also see, then also I would require 3 only. Like I, let's say A is 1, 0, 0, 0. For B, I have to write again. Oh, so he says that. Okay, okay. So my because of this constraint, let's say if I'm bringing a constraint to it, so because of this constraint, my dimension is reduced, right? My dimension is reduced now. So if I want to write B, it will be 0, 1, 1 and 0, I think. So because of the constraint, the dimension has reduced. Because of the constraint, the dimension has reduced. Is that clear? So here it is reduced. See, now you can span this particular space by only these two vectors. Okay, so if I take d certainly 0, then obviously I'm bringing a constraint. Okay, if I'm bringing a constraint, then dimension is bound to get reduced. Is that clear? Okay, so that happens. I mean, if you are bringing some linearly independent constraint, then dimension gets reduced. Okay, if you remember that initially we were writing that trace should be equal to 0 or such kind of things we are writing. So are you getting my point? Okay, chalo. So let us go a little bit further and write a few more dimensions and things like that. Okay. Okay. Just a small question for you. Small question. Do you think that this forms a subspace? Do you think that this forms a subspace? Okay, so I'm writing for you the subspace, and just try to think that whether this forms a subspace or not. Okay, so if I take a set S, uh, and that is the set of all polynomials with degree exactly p, exactly k, where k belongs to natural number, or okay, in the vector space pk, in the vector space pk, in the vector space pk, does S form a subspace? Does S form a subspace? See, always remember, I have already taught you that if I am writing a set of polynomials, with degree at most k, with degree at most k, then this forms a set of this forms a vector space. If you remember, this forms a vector space. This forms a vector space. Okay, pk means what? Pk means set of polynomials with degree at most k. So if this is the case, then it forms a vector space. That is very much sure. I'm now saying, because in this particular set itself, see, in this particular set, what all things would come? Identity would come, 0 would come, obviously. When I'm writing at most k means what? Polynomials with degree less than equal to k will be allowed. So even the 0 polynomial will be allowed. Okay, you will have some polynomials in form of x, simply x square also. I'm not writing the entire stuff. There would be polynomials in terms of xk. So all these kind of polynomials would be there. So obviously these kind of polynomial with degree exactly equal to k would be there. So now I'm making a subset out of it. I'm making a subset where I have only polynomials of degree k. Now I'm asking, does it form a subspace? So let me take an example and understand. Let me give you an example to make you understand that this does not form a subspace. This does not form a subspace. Why? See, just take an example of what should I take? Let us take an example of x ki power k plus 1. So clearly, one of the elements p1 can be this x ki power k plus 1, right? This is one of the elements exactly equal to like exactly degrees k only, exactly the degrees k. And if I take this degree and let us say that in pk is what? It is a vector space of polynomials with degree at most k. So in this particular vector space, the identity element will be the zero polynomial. The zero polynomial will be contained in pk. Okay, what is a zero polynomial? Zero polynomial will be contained in the pk. Okay, so this is simply a zero function, or you can say a polynomial of degree zero. Polynomial of degree zero, and in general, bit is zero, just a zero. Okay. Just everything is happening today. Okay, so okay, this is a polynomial, zero polynomial, that is polynomial of degree polynomial, that is zero polynomial. Okay, zero polynomial, that is polynomial of degree zero, and the coefficient is also zero. Degree is also zero, and the coefficient is also zero. Okay, so this would be contained in pk, but is it contained in this? Is it contained here? Is it contained here? No, clearly no, because it contains all the polynomials with degree k. It cannot contain the zero polynomial. So P1 does not contain P1 does not contain zero polynomial. And since it does not contain a zero polynomial, it does not contain the additive identity. And since it does not contain an additive identity, what does it imply? It implies that P1 is not a sub PK, or you can say I've written PK, which is like a set S, which only contains the polynomials with degree exactly k. Polynomials with degree exactly k. They don't form a subspace. They don't form a they don't form a subspace. Is that clear? I hope it is clear. Now let us come to one of the important topics in linear algebra. What is a zero polynomial? Okay, zero polynomial is simply zero, zero. See, whenever we write polynomial, a1x plus a2x square plus a3x cube dash 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 anxn, right? This is your polynomial of degree n. Okay, now it will contain all these terms. Let's say if I'm saying in the set of polynomials, if I'm rejecting this, rejecting this, rejecting this, rejecting this, I will after all get a constant function also. So constant in general is also polynomial. Constant in general is also polynomial of degree zero. Okay, so you see, if I write a n equal to 0, obviously, if I write a n equal to 0, then this will become the polynomial of degree n minus 1. If I write a n minus 1 equal to 0, then this will become polynomial of degree n minus 2. And if I so on write all these higher powers as 0, at the end I will be left with this a naught only. And what is a naught? A naught is a constant function. So constant function in general is nothing but a specific case for your polynomial only. Okay, so this is called as a zero polynomial. Okay, always remember, whenever I have to negate, this is a very good idea, that whenever you have a vector space W and you have a subspace W, and you want to prove that, or you want to disprove that W is not a subspace, just see that the additive identity here is contained here or not. One of the ways to counter it is that just see whether the additive identity is here or not. If the additive identity is not here, then it is useless. Okay, then why it is not contained? See, when I'm saying pk, what does it imply? Pk implies set of polynomials with degree at most k. At most k मतलब at most k means what? When I'm saying degree pk, it is less than equal to k. Now I'm talking of another set where I'm very strict. I'm saying exactly k. When degree is exactly k, how can I have this zero polynomial here? For zero polynomial to exist, the degree should be 1. A degree should be 0. Here you have this freedom. When I'm writing at most k means what? All the polynomials with degree k minus 1, k minus 2, dash dash dash, p2, p1, and even 0 would be contained here. The zero polynomial would be contained here. But here the zero polynomial cannot be contained. When I'm writing that I only want polynomials with degree exactly k. So how would zero polynomial be contained here? So obviously this does not contain an additive identity. That is also, we can say that it does not form itself a vector space. What is a subspace? Subspace is a subset of a vector space which itself forms a linear vector space. But here it does not form a linear vector space because it does not have an additive identity. Are you getting my point? When I'm writing exactly k, I'm talking about polynomials with degree exactly k. So this set will not form a subspace. Is that clear? Okay. See, understand the point. See, if I'm saying I'm considering only polynomials with degree k, let us, for example, write this only for simplicity. Now just think what would be zero function here. There is no zero function contained here. Okay. Zero function is simply zero. Uh, I would say, what is a zero function? Zero function is simply zero for all x belongs to R. I'm not saying keep zero. Oh, that is not the case. I'm saying zero function is zero for all x belongs to R. So it is not contained here. For us, what is a zero function? Zero function is, after all, this. This is your zero function, right? Is it contained here? So zero function is not contained here, because for zero function to be contained, it should be having degree 0 here. However, when I'm saying polynomials of degree k, it implies I will have only polynomials of degree k. Let us say I'm saying polynomials of degree 2. It implies what? I will have this only, ax square plus bx plus c. Right? Only this. But when I'm saying that 0 is contained here, how come 0 is contained here? 0 is not contained here. If I'm saying polynomial of degree less than equal to 2, if I'm saying polynomial of degree less than or equal to 2, then it is fine. Then I'm talking of this space where you have ax square plus bx plus c, you have mx plus c, and then you have some constant functions. See, understand, what if a constant is added to it? See, even if you add a constant here, I'm just saying, see, I have to write, for any vector space, you must have a, see, for any vector space, what you should have a zero function, right? Or you should have an additive identity, and this additive identity must be contained in this set. Okay. Now I'm saying, let's say this is your the most like this is it. Okay. Now tell me, if I add xk plus 1 to what? so that I get xk plus 1. It should be a zero function indeed. Okay, zero function. When I'm saying zero function, what does it mean? It means that I'm adding a zero. Zero means what? It is a polynomial of degree zero. How come polynomial of degree zero contained here? Don't say that this is constant. No, obviously this is a constant. I'm not saying that. Understand, this is a polynomial of degree k. So additive identity should come from the set itself. It cannot come from outside the set. So whenever I'm saying that, let's say V is a vector space, if I'm saying if forms a vector space, then a plus 0 element is equal to 0 plus a is equal to a. This 0 should be a element of V, set V. Now what is this 0? 0 is a, see, we use 0 at different point of time. Let's say for matrix we use 0. That implies I'm talking of this. Okay. Okay. Are you getting my point? For let's say for functions, when I say 0, it means zero function. Zero function means what? I'm talking of a constant function which is 0 throughout. Now understand, this particular function is a polynomial of degree 0. One is here, I understand, but it is not constant. This particular entity is a polynomial of degree k. You cannot separately say that one constant is contained. Okay, you will say that this is a polynomial of degree k. This is a polynomial of degree k. Now just tell me whether there is an identity element in polynomial of degree k. Exactly k, I'm saying. Exactly k. If I had written less than equal to k, then all the polynomials lesser than equal to k would come. So for example, having degree lesser than or k would come. And in that particular thing, you will have a you will have a zero polynomial also. But when I'm specifying that it is equal to k, then things won't work. Uh, is that clear or not? See, whenever I'm saying polynomial of degree less than equal to n, what does it imply? It implies I'm talking of polynomials in x raised to power n, which will contain all those terms. It implies that I can have polynomials in degree n minus 1. It implies that I can have polynomial in degrees x square. It implies that I may have a polynomial linear. It implies that I may have a constant also. Okay, why can't we take 0 into xk? Okay, so this is by definition. See, the student is asking that can't we take can't we take this x polynomial of degree k in this fashion? And let us say that ak equal to 0. No, that is not. This is not. This is by definition of the polynomial that ak should be non-zero. See, whenever you are stating this, I'm stating that I am talking of a polynomial of degree n. What does it imply? It implies I am talking of this thing. And whenever we write this, the time we write this, we say that an must be non-zero. Because if an is 0, then it is no longer a polynomial of degree n. Then it is a polynomial of degree n minus 1. So by definition of polynomial itself, this coefficient can never be equal to 0. Is that clear? So always remember, if I had made a mistake, I'll see back in the lectures also. Always remember, polynomial of degree less than equal to n forms of less than equal to n forms of vector space. If I had made a mistake, then I'll correct it. Don't worry. Okay, it forms a vector space, but polynomial exactly of degree n does not form a vector space. It cannot form a vector space because for a polynomial of degree exactly equal to n, there would be no identity in this, because additive identity is what? Additive identity after all is a zero function. And what is a zero function? Zero function is a polynomial of degree 0. How can it be contained in this set? It can never be contained in this set. Having some constant added to it is a different thing altogether. That is, see, for example, if I write x raised to power n plus 1, x raised to power n plus pi, or x raised to power n plus x raised to power n plus e, or x raised to power n, simply all of them will be counted as a polynomial of degree exactly n. Okay, but understand in this particular set 0 is not there. 0 is not here. What is 0? 0 function hai. It's not that I can place 0 or not. No, that is not what I'm saying. I'm saying that whether 0 function is there or not, 0 function is completely 0. That is for all x belongs to R, it should be 0. Is that contained in this set? No, no, not at all. It cannot be contained in this set. Because if it is contained in this set, then it is violating the definition of degree n. I hope it is clear. Okay, so after this discussion on subspaces and everything, let us come to something called as linear transformations. And this is an important topic. So I'll start with this today. Linear transformations. See, at times, till now we have understood what is our vector space and everything. Now we'll be talking about the mapping between the two. Now we'll be talking about the mapping between the two vector spaces. Okay, and these certain mappings are called as the linear transformation. So now we'll be talking about mappings between the two vector spaces. And these certain mappings are what is known as your linear transformation. And what is that certainty about them? There is some conditions that we'll impose. There is certain conditions that we are going to impose. Okay. In fact, in physics also, you know that from one vector system to another vector system, you have to go. Okay. This also require a one coordinate system to another coordinate system if you want to go. This study requires something called as the linear transformations. This study requires something called as the linear transformation. So let us consider mapping, and you will be able to understand what I want to convey. Consider a mapping, and what it will do, it will transfer any plane vector in R square to a space vector in R cube. What it is going to do, it is going to convert any plane vector in R square into a space vector in R cube. How come? See, if I define a map from R square to R cube, let us say I want to say that put xy here and give output as xy comma 0. So what is happening? I'm taking an input in R square, I'm reverting you R cube. So let us say this is a mapping. So clearly this belongs to R cube. This is an element in R square. Okay. Is that clear? Now just consider two of the things that I'm writing. Just try to find what would be f of a plus b plus c plus d. So it will be equals to what? It will be equals to f of a plus c comma b plus d. And it would be equals to what? It would be equals to a plus c comma b plus d comma 0. So what it is going to do? It is going to convert any vector in R square into a vector in R cube. So this is what? This is vector in R cube. This is a mapping. This is a mapping that I'm saying. What am I going to do out from this mapping? I'm going to I'm going to transform a vector in R square to a vector in three-dimensional space. Is that clear? Now I can write this as a comma b comma 0 plus c comma d comma 0, right? I can write in this fashion also. Also consider another operation that I'm saying. Just try to multiply inside by alpha. And let's say alpha belongs to R, and I'm doing this. What am I going to get? I'm going to get f times alpha a comma alpha b. And what am I going to get? I'm going to get alpha a comma alpha b comma 0. Please understand the mapping says what? Any ordered pair, if you are supplying, you will get a triplet here. I mean, what you can say, three tuples here. Okay, and I can write alpha a comma b comma 0. So there are two distinctive properties that you can see. There are two distinctive properties that you can see. Two distinctive properties that you can see, that if I supplied two vectors here, u1, u2. What did I get? I got fu1 plus fu2. And secondly, if I supplied this alpha u, you got what? Alpha times fu. These properties are called as the properties of linear transformations. And the same property you are going to you are going to write for your linear operators. Lately in quantum mechanics, we are going to write these things as the properties of linear operators. That is, if I am saying that I am talking about a linear operator, what do I mean by linear operator? It will hold these two functional relationships. That if I am going to supply a sum into it, then I get the sum of the images. And if I'm going to apply uh, a scalar product inside, I'm going to get the scalar product of the image. Is that clear or not? I'm going to write it. So basically what has happened? So because of these transformation, what has happened here? What has happened? So here I took the sum of two plane vectors, sum of two plane vectors. Where did it get mapped to? It get mapped to the sum of their images. And what are their images? Their images are nothing but the space vectors. Is that clear? Or is that not clear at all? Okay, so this is the kind of transformation I'm saying. So what does it, and the other one is, what did I supply here? If I write a comma b, basically I'm writing a vector. Basically I'm writing a vector. So it is a I cap plus b j cap kind of thing. So you can say that a line in R square has been mapped to a line in R cube now. Is that clear? So this is what ai cap plus g cap k cap plus c k cap. So basically what has happened, let's say I was discussing initially a rectangle here in 2 dimensions. And what has happened after this transformation? If I apply this transformation, that is f of x comma y is simply x comma y comma 0. So what now I would visualize this as, I'll visualize it in this fashion now. This is x, this is y, and this is z. It says that your z coordinate must be 0. Your z coordinate is 0 means I'm going to visualize this here. So now I'm talking of a square in 3-dimensional space after this transformation. This transformation happens to be a linear transformation. Because I told you that the properties that I actually worked out for you, they formally I'll define later on, but these are the properties for the linear transformations. Is that clear or not? Please let me know if that's not clear. If it's clear, then I will straightway come to the formal definition of a linear transformation. And this has got wide, big applications in physics. So please keep in mind all these things, because lately we are going to write the matrices of linear transformations, and that corresponds to your matrix representations in quantum mechanics also. So please let me know if it's clear. If it's not clear, please let me know it's not clear. I'll repeat it all over again. Don't worry. It can be constant also. Don't worry. See, in any case, we have to verify. See, we have to verify. That I'm going to tell you. That I'm going to tell you. Just keep little bit of patience. I'm going to write definition, and then we'll see. Yeah, then we'll see. See, even if you add a constant, then things may change. Then things may change. Then things may change. So I'll do it for you. Don't worry. So right now, just keep in mind that what is a linear transformation after all? Then things may change. Don't worry. If it is non-zero, then things may change. So let me do it for you in the next case itself. But let us first write what are linear transformations. What are linear transformations? Okay, let us first write the definition for linear transformation. So I'm writing that let U and V be two vector spaces. Okay, so R cube is a vector space, R square also form a vector space. Okay, so let U and V be two vector spaces And we'll come to the question that Bharat is asking, but let us first write the definition. So let U and V be two vector spaces over a field F. Okay, a linear transformation or a linear operator. Okay, so in quantum mechanics we are going to say it linear operator, but right now I'm writing mathematically it is called as a linear transformation. In quantum mechanics we are going to write the same things for linear operators. Okay, a linear transformation is one, not one, I should write, from U to V is a function, from T, is a function T from U to V, such that if I take two, uh, like like here U1 plus U2, it will give me T times U1 plus T times U2 for U1, U2 belongs to U, and T times alpha U is equal to alpha times Tu. It will be alpha times Tu, where alpha belongs to F. Where alpha belongs to F and U belongs to U. Okay, is that clear? Okay, and we can shorten these two conditions by saying this also. Or if both of them, if you don't want to see, if you just want to see one condition, then you can in combination write this, that if you find that T times alpha 1 U1 plus alpha 2 U2, it is equals to alpha 1 Tu1 plus alpha 2 Tu2. Okay, so alpha 1 Tu1 plus alpha 2 Tu2. This is what you're going to get. Okay, if these two conditions are true, then always remember that that we are talking of something called as the linear transformation. See, additional some conditions follow. So I'm writing additionally some conditions follow from here only. What those can be? So if I want to find the linear transformation of a zero, then it will be always a zero. Then it will always be a zero. See how? What is zero? I will write 0 plus 0 here. It will be t0 plus t0. It implies what? T0 should be equal to 0. So this is the first thing. I have applied just linear transformation here because 0 is what? 0 plus 0. I can say if it is a linear transformation, then it will be t0 plus t0. That implies the function, that is the transform of 0 would give me a 0. Linear transform of 0 would give me a 0. And 0 is what? 0 element in U. This is 0 element in U. Okay. And if I want to find like inverse element in U, let's say for, since U forms what? U is a vector space. So for every U belongs to U, there would be minus U belongs to U, right? So what would be T minus U? It would be simply minus of TU. It also follows from the above condition. That is, if I take alpha is equal to minus 1, so T times alpha U should give you alpha times TU. So all these things are defined from the initial ones only. And this will help you and understand the question that Bharat is asking. Okay, so I'll come to that also. Okay, now first let us take the case of identity transformations. Okay, so what does identity transformation means? I'll just write it as IU or simply identity. What it is? It is simply T defined from U to U. Means what? If I use an identity transformation, my domain U will become the entire U only. And what is the transformation like? You supply me any U, I will give back U. Okay, Tu is equal to simply U. Now, let us say that alpha and beta belongs to field F over which this U is a vector space. Then T times alpha U plus beta U is equals to alpha U plus beta U, and which is equals to what? which is equals to, I'll take u1 u2 so that things are more generalized. Okay, and this is equals to what? This is equals to alpha times tu1 plus beta times tu2. Is that clear? This is from the definition. That is t. If I supply alpha u1 plus beta u2 inside, it will give me alpha u1 plus beta u2 here. And if I want to write what is alpha u1, it is alpha times tu1. What is beta? Beta is beta times tu2. So clearly I can say that t forms a linear transformation. That is, we can say that identity is a linear transformation. Okay, now let us come to another point. So as I told you, there was a null transformation initially. So let us now write zero transformation or a null transformation. What does it do? It will make, and the image of this, any of the u would be exactly zero. A null transformation. Okay, so let us say that t is defined from u to v, and such that t of u is simply 0 for all u belongs to u. So this is what is known as your null transformation. Does it form a linear transformation? Let us see. Does it form a linear transformation? So let us say alpha and beta belongs to field f, and let's say u1 and u2 belongs to u. Then t times alpha u1 plus beta u2 would be equals to what? It would be equal to 0, or you write it as alpha times 0 plus beta times 0. This is one and the same thing. Or you write alpha times tu1 plus beta times tu2. So clearly, this null transformation or zero transformation also is a linear transformation. Now let us take another transformation which is called as the projection. So I'll usually pi is used. Okay, I'll use p something like prj from Rn to R. Now what does, sorry, what does projection j, the subscript is j here. So what does this do? What is Rn? The elements in Rn would be x1, x2, x3 dash 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 somewhere xj, then xj plus 1 dash 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 xn. If I'm applying a projection here, so it will give me the projection along the z, along the j axis, along the j axis. So this will return me xj. If I say what would be pr1, so it would return me the coordinate, or you can say it would return me the top, this first one. This is x1. So this is the projection along like E1. This is the projection along the E1. This is a projection along E2. Okay, this is what you do now. Let's say you have 3, 4, 3, comma 4. So what is 3, comma 4? After all, this represents 3, comma 4. It represents what? 3 is what? 3 is the projection along x-axis. What is 4? 4 is the projection along y-axis. If I generalize it into Rn, then all of these like x1, x2, x3, all of these tuples are what? All of these tuples are nothing but they are the projection along the standard basis vectors. That is E1 cap, E2 cap, E3 cap, so on and so forth. So what does PRJ do? PRJ would return me xj. PRJ would return me xj. Let's say for example, for 3 dimensions, and if I'm doing PR2, and if I want to write from R cube to R, what it is going to return me? It is going to return me the yth coordinate. Okay, because in xyz in R cube, if I apply PR2, what is it is going to return? It is going to return me simply y. Okay, is that clear? I hope it is clear. And if it's not clear, please let me know. This is called as the projection transformation, or you can say simply projection. Okay, this is known as the projection transformation on the jth coordinate. So do you think this forms a linear transformation? I mean, is that clear, or is there something that people are not able to follow? See, projection, this particular projection function, you can say, or you can say projection on the jth coordinate forms a linear transformation. This also forms a linear transformation. This also forms a linear transformation. Let's see how. So let us take one simple example and then let us do. Let us take, for example, we are talking, let's say, of PR1. So we have to prove that PR1 forms a linear transformation or a linear operator. How to do so? Let us take two tuples x1, x2, n tuples. One is this xn, and let's say this is x, and let us take another y, which is simply y1, y2, dash dash y. What I'm going to do, I'm going to do PR1 alpha x plus beta y. It will result me into what? It will result me into alpha x1 plus beta y1. See what it is going to do. Alpha x plus beta y. Do you understand what does it mean? It means that I'm trying to find the projection along the first coordinate. And what is alpha x and plus beta y? Alpha x is simply multiplying all these things with alpha. Beta y is multiplying all these things with beta. This y. So what is beta y? Beta y would be beta y1, beta y2, dash 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 beta y. What would be alpha x? Alpha x would be what? It would be simply alpha x1, alpha x2, dash 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 alpha xn. Okay, now if I just do this way, alpha x1 plus beta y1, comma alpha x2 plus beta y2, and so on and so forth, and if I write alpha xn plus beta yn, and if I'm applying the projection along the first coordinate, what I'll get in return? I'll get this only. And what is this, by the way? This is simply PR1 alpha. You take common out and you just write PR1x and beta PR1y. So clearly you can see that PR1 is a linear operator. In general, always observe, we can observe that in general, PRJ, that is which represents the projection on the jth coordinate, or is a linear operator. It is a linear operator. Is that clear or not clear? Uh, is that clear? I don't know. Please let me know if that is clear. If it's not clear, then please write it's not clear. At least I'll not go further then. Okay, so let us discuss some other projections. So what is other? Just give me a minute now. Okay, so let us discuss some other projection. So some different projections. What these projections are going to do? Let us say the first one that we discussed. If I want to project my r cube to r square, what it is going to do? So this kind of projection, let us define it as x comma y comma z, and it will be equals to simply x comma y. So this is the projection of us. You can say from r cube to a plane. This is a projection of from r cube to a onto an xy plane. So what should I write? So this represents projection from r cube to r square, or you can say to the xy plane simply. Okay, so this is one another kind of projection. Okay, similarly you can define some other functions like let's say q x comma y comma j, and it projects you into, let's say, xz plane. So these are another kind of projection. So these are also called as the projection map. I'm not writing subscript here, only projection map. And what was that? It was PRJ, which is projection on the jth coordinate. PRJ, if I'm writing a subscript, it represents a projection on the jth coordinate. And if I'm just writing this, this is called as a projection map. Always remember, this also forms a linear transformation. This also forms a linear transformation. Let us take another example that we did in matrices also. If you remember, in matrices we tried to write about reflection matrices. And reflection matrices are one. You would have seen that in reflection matrices, the determinant is equal to -1. If you remember, we've done the reflection matrices also. And let us take an easy example. Let us consider reflection uh, what you can say, taking x-axis as a mirror. Okay, reflection, uh, you can say in the x-axis. Yeah, you can say taking x-axis as the mirror. So let me take an example. So this is your x-axis. Let's say if I take a point here, uh, let's say general point. Let's say general point x comma y. I hope you will not get confused with this. This is simply x-axis. Okay, so this is, let's say, x-axis, capital X. Okay, and let us say this is your capital y-axis. Okay, if you're taking the reflection over this, so what you're going to get, if I take a reflection exactly equal to, I will have the image of this. So x will remain x, but y would becomes -y. This is a linear transformation, isn't it? Is it a linear transformation? Let us see. So this is a map from r square to r square. And how I'm going to define it? Just supply me x comma y. I'll give you the reflection along the x-axis, which is x comma -y. You just give me any xy. I will give you a map. I will give you a reflection of that particular point along x-axis, which is x comma -y. We want to see that whether it forms a linear transformation or not. Whether reflection along x-axis forms a linear transformation. Okay, it does form linear transformation. See, if let us take 2 points x1 y1 and x2 y2. So I'm going to write directly. Let us take 2 points alpha x1 times beta x2 y2. See what it is going to return me. It is going to return me. Uh, uh, I will write simply t. I will simply write alpha x1 plus beta x2 comma uh, alpha y1 plus beta y2. This is how I can write this. And if I am applying this, what I'm going to get in return, I'm going to get the x-axis as it is. And then the y coordinate will be multiplied with the negative sign. Is that clear? Or what I can do, if I want to write this up, I can write x1 comma minus y1 plus beta times x2 comma minus y2. Okay, and certainly this is what, this is t times what should I write? I should write it as u1. Let's write u2. So this would be t times u1, and this would be simply beta times t times u2. So clearly you can say that t is a linear operator, or you can say linear transformation. And please understand what is t. T is simply your reflection. Okay, now let us say another case where you want to translate something. You want to translate something. Let's say, what should I say? Let us say that I want to translate something by a constant vector. Okay, so translation by a constant vector, constant non-zero vector. Okay, constant non-zero vector. Let's say u naught. So let's say if I'm saying that, and I'm not writing a vector here. Okay, in general u naught. Okay, so let's say. Uh, let us say that u naught is a fixed non-zero vector here, non-zero vector. Okay, non-zero vector. Okay, non-zero vector. And what I want to do, I'm defining a linear transformation from u to u. And what it is going to do, it is going to translate my vector supplied by a constant vector u naught. So what does it mean? Let's say if I have a rectangle here. Okay, let us say I'll write something 1, 2, 3, let's say 4. Okay, so this is 1. And if I want to translate this by 1, 1, so I'm not writing vector here, okay, because I'm using the general notations. So if I want to translate it, through minus 1, 1, 1. So if I want to translate this rectangle by, I want to translate this rectangle by vector 1, 1, what it is going to, so the x-axis will be translated by 1 and y-axis will also be translated by 1. So I will write something here so that you will be able to understand that what I am trying to explain. So this is, let's say this is 1, let's say this is 2, and let me increase it. Let us say this is 3, and all the more. So let's say this is 4. So what this particular translation is going to bring about? So now your new what you can say rectangle would be translated by 1, 1. So by translation by 1, 1 I mean, okay, instead of 2, first thing that it will start, sorry, instead of, let's say here it is 2, it will start from 3. And the y-axis is also, so 1, 1 means what? So along x-axis also 1 would be added, along y-axis also 1 would be added, right? Just give me a minute. Okay, so I should take a eraser and then strike it out. I don't know how to. 1 minute. Just give me a minute. Where did that go here? Eraser, eraser, eraser. I don't know where does eraser goes. Just give me a minute, okay? I think. I don't know where does eraser has gone. Okay, so what I want to convey is that this is not the, this is not what I want to say. This is eraser. Okay, this is eraser. Okay, so okay, so by translation, what will happen? By translation, my rectangle would go this way. So let's say this is my original rectangle. Because 1, 1 would be added, so basically what it is going to, it is going to translate along x-axis by 1 and even along y-axis by 1. So this is how my translation would take place through point 1, 1. Okay, is that clear? So this is a translation vector. This is a translation, you can say, one of the transformation that I want to do using a non-zero vector. This is a non-zero vector. Now question arises that whether it is a linear transformation or not. Whether it is a linear transformation or not. So answer is no, it is not. It is not a linear transformation. Why it is not a linear transformation? So if you remember, if something is a linear transformation, let's say tu1 plus tu2. If t is a linear transformation, then tu1 plus tu2 should be equals to what? It should be equal to this. And what should be alpha tu, uh, alpha times u? It should be alpha tu. Okay, these are the two conditions for t to be a linear transformation. And if you remember, what did I do? Whether you write alpha equal to 0 or you take both u1 and u2 equal to 0. You take both u1 and u2 to be equal to 0. Okay, you take both u1 and u2 to be equal to 0. So what do you get? You get t of 0 should be equal to what? 0. So here, let's say t is equal to 0. If I take t is equal to 0, then t0 should be equal to 0. But what is the transformation like? But I know that tu is equal to u plus u naught, and u naught is a non-zero vector. If I apply here 0, what I'm going to get? I'm going to get u naught, and which is certainly non-zero. It implies what? It implies that this translation is not a linear transformation. It is not a linear transformation. It is not a linear transformation. Is that clear or not clear? I hope it is clear. Please let me know if it is not clear. Okay, so okay, now let us do another case. I have done reflection along x-axis. Try to do reflection along y-axis. Whether this forms a linear transformation or not. So let's say if I want to define a transformation from r square to r square, which represents the reflection along y-axis. What is reflection along y-axis? Let me take. Okay, so sorry. See, what I did was I wanted to translate a square by a vector 1 1. A vector 1 1 would mean what? It means that if I want to translate using this is, let's say, my translation, what you can say. This is my translation function. That is, if I supply a u to it, I'll add a non-zero vector u naught to it. And let's say if I want to just visualize it, let's say if I want to translate it using 1 1, what does it mean? The x coordinate would be appended by 1. That is, the x coordinate would be given a additional x plus 1, and y would also be y plus 1. So basically, this is how your square would translate through a non-zero vector 1 1. This is just for an example I'm saying. I hope you remember that uh, that if t0, if I want to find, and if t is a linear transformation, then t0 should be equal to what? It should be simply equal to 0. Okay, obviously this is r square, so 0 would mean 0 comma 0. R square would mean 0 comma 0. But understand, t0 should be equal to 0. If it is a linear transformation, t0 should be equal to 0. t0 should be equal to 0. But what is happening here? If I take u equal to 0, on the left hand side I will have a 0 because t0 is 0. Since if I am claiming that it is a linear transformation, then t0 should be equal to 0. This is from the definition of the linear transformation itself. Okay, for r square, you know that the additive identity would be what? 0 comma 0. So this is your 0 element in r square. Okay, not exactly 0, but I mean origin 0 comma 0. Now if I put 0 here, what I'll get? I'll get 0 plus u naught, and u naught is a non-zero vector. So clearly there is a contradiction. So t cannot be a linear transformation. T, that is a translation with a non-zero vector, cannot be a linear transformation. Is that clear or not clear? I hope it is clear or not clear. Please let me know. Okay, is that clear? Now I'm taking reflection in the y-axis. Okay, now I'm taking reflection in the y-axis. So if you remember, I took reflection on the x-axis. Now I'll take reflection along y-axis. And I think this would be the last thing today. Then we'll do more questions on linear transformations tomorrow. But please remember, this is an important thing. This is an important concept. Okay, because after all, quantum mechanics is all about understanding linear operators. Okay, linear Hermitian operators. So that's why I'm focusing on this, the course of linear algebra. Although I'm just skimming through, I'm not teaching you in very detail. But okay, uh, for physics I can take that liberty. Okay, so if I want to do this, what it will be, the point, if I take a reflection along y-axis, it would be equals to minus x comma y. Now this is my transformation. That is, if I supply my point t x supply my point x comma y, the image I'm going to get minus x comma y. So this is the linear transformation. Sorry, is it a linear transformation? The question is it a linear transformation? The answer is yes, it is indeed a linear transformation. Let's see how. So if I take 2 points alpha x1 comma y1 and take another point x2 comma y2, what am I going to get? I'm going to get t times t of alpha x1 plus beta x2 comma alpha y1 plus beta y2. So what it is going to return me? It is going to return me minus alpha x1 minus beta x2 comma alpha y1 plus beta y2. And what this is equal to? This is equal to alpha times minus x1 comma y1 plus beta times minus x2 comma y2, and which eventually is equals to t times, let's say this is your u1, let's say this is your u2, this is t times u1 plus t times nahi yaar, t of u1 plus beta tu2. So clearly I can say that this is your t is a linear transformation. So I hope to meet you tomorrow with all the more questions focused on linear transformations. Okay. Please keep in mind these are very important concepts. And as we go along, we're going to see a little bit more of things like matrices of linear transformations. And all these things you're going to see as a structure in quantum mechanics. So therefore, I'm teaching you all these things because after all, this linear algebra is going to make a lot amount of your structure part of quantum mechanics. Okay, so I hope to meet you tomorrow. Till then, take care. Bye bye.